In this video, we're still going to be talking about capacitors. But under capacitors, we're going to be talking about capacitors when they are arranged in series and in parallel. Okay. Now, the first question most students ask is how then do you identify when capacitors or cells in general are connected in series or in parallel? Now, here is a good understanding. That is why you're having two different diagrams on the board. Now, when they are connected with a single wire, okay, on a straight line, okay, it could be straight or curved though. But then if you notice that it is a single wire, just like what we're having here, from here to here, okay, all cells or capacitors or resistors, anyone, with this you're talking about capacitors, okay? So when they are connected with the same wire, they are said to be in series. That is also what we're having here. So if they are connected with the same wire, they are said to be in series, okay? While in parallel, or rather for parallel connection, you see how they are being arranged, okay? They are arranged in such a way that each capacitor is parallel to the other one. Okay, that is how it is being done. Each one is parallel to the other one. Although there are sometimes you notice that they are not parallel, but then they are curved. Okay, so you still might be wondering why they are called parallel capacitors. Okay, that is because the first set of arrangements we had, they were arranged in parallel. Okay, although we could as well bend this tip, okay, even if they are not touching, but then they will be bent, and then we'll notice if we trace the line, they will touch. Then we'll still call it parallel. Yeah, we're still going to call it parallel. Okay, you just have to notice that if you try to straighten them out, you're going to have capacitors in parallel. So even if they are curved, you can as well draw a new diagram for each of them. Okay. Now, how then do we find the next capacitor or next capacitance rather for parallel and series connection, just like resistors? Okay. When resistors are arranged in series or parallel, we tend to add on each of the values. Now, do we do the same thing for capacitors in series and parallel? We're going to find out. Now, for capacitors in series, what you should take note is that since they are connected with the same wire, the same charge is going to flow through them, okay? Same charge is going to flow through this what now? This capacitor. Hence, we can say that the charge in C1 is equal to the charge in C2, charge in C3, down to as many number of charges capacitors we're going to have. Let's say Cn, okay? Infinite number of capacitors we are having, okay? Now, the potential difference for each of them is going to be different, okay? Take note. V1, V2, V3 represent the potential difference for each of them, okay? Now, why is it going to be different? Because we're assuming that the capacitance is going to be different for each of them. The only time it's going to be equal is if we're having equal capacitance. That is, we're having C1 equals C2 equals C3 equals C4, blah, 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 down to Cn, okay? So we're assuming they are not equal in this case. So only the same charge is going to flow through them. And C1 and V1, they're going to be what now? Different from the other values. Now, in this case, since we know that V1, V2, V3 down to Vn represents the individual voltages for each of these capacitors, simply means if we take the sum of these voltages, we're going to get back the voltage that is being supplied, okay? Right? We're going to get back the voltage that is being supplied, assuming that these wires, they are having negligible resistance and capacitors as well, okay? So we're going to neglect all of these considerations, okay? So it means we'll add V1, V2, V3 down to Vn, we're going to get what now? V. It simply means that the total capacitance V will then equal V1 plus V2 plus V3. I'm going to add as many number of capacitors we're having plus dot 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 plus, let's say we're having Vn. Okay, that's how it is being done. Now, we just understood that to get this voltage, we simply want to take the sum when they're in series, right? Let's plug this formula and see what we can arrive at by manipulating some of these values we're having here. Now, we need to recall that from our previous video, and then we know that the capacitance of a capacitor, okay, the capacitance of a capacitor C is equal to the ratio of the charge to the voltage, right? So it's equal to Q over V. If we choose to substitute into this formula, we're going to get, we make this subject formula, okay, I'm going to get V equals Q over C. If we choose to substitute that in, we'll get Q over C, that is the total charge in the capacitor divided by the what now? The total capacitance, okay? And that is going to equal V1 will now be the charge in the capacitor divided by the capacitance, which is C1, plus V2, the charge in the capacitor divided by the charge C2, plus V3, charge in the capacitor divided by charge C3, plus we're going to continue like that, plus charge in the capacitor divided by what? Cn, right? Now, you notice that For the capacitance, I indicated them with the numbers 1, 2, 3 down to n, okay, to infinity. But then for the charge, I did not put the numbers. Why didn't I put the number? Okay, you might want to pause the video and think about it. But then I said initially, before I started doing this, okay, before I started doing this, I said since they are connected with the same wire, the same charge is going to flow through them, just the same way current is going to flow through them cells if it were to be a resistance. Okay, so in this way, the charge is common between all of them. Okay, we can factorize this out. Okay, so we're going to get Q divided by C. We're going to get Q divided by C is equal to, this charge is common, so we can bring it out. We have Q in brackets, and we have 1 over C1 plus 1 over C2 plus 1 over C3 plus dot 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 plus 1 over Cn. Okay, that's what happens. Now, charge is common to both sides. They can both cancel out, and then we're left with what now? 1 over C. So we can then say that for a capacitor in series, the net capacitance can be calculated by using the equation 1 over C, or I can write that C total to tell you that this is the net capacitance. It will equal taking the sum of the reciprocal of each of the capacitors, 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4 down to Cn. Okay, so I can well just write it like this, plus dot 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 plus 1 over Cn. Okay, so here is the formula for doing that, and this is how it is being done. Okay, so now for capacitors and series, you simply have to take the reciprocal of each of the value of the capacitance, okay, and then take the sum, and then take the reciprocal, because we're having 1 over C. After doing solving with this formula, we still have to take 1 divided by the answer to get our value. Remember, it is measured in farad, most times in microfarad, most times in picofarad. Okay, now how about for capacitors in parallel? How then do we deal with capacitors in parallel? It is quite similar, you just have to understand the concept. Now for capacitors in parallel, you should take note that when capacitors are connected in parallel, they form what we call an equipotential surface. That is, the potential difference at each capacitor is then what now? Equal. So we can simply say that the potential difference here could be V, and as well here V, and all throughout the capacitors that are arranged in this line of parallel capacitors. Okay, now how about the charge? The charge across each of them will be different, so I can as well come here to say here we have Q1, we have Q2, we have Q3, and then we'll have Qn. Okay, so what then will become the net capacitance, and how are we going to solve for it? Now, to doing that, we are going to follow the same procedure to get the net charge. In this case, to get the net charge, we're going to say the net charge Q is equal to Q1 plus the charge Q2 plus the charge Q3 plus dot 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 plus the last charge. We're going to get Qn. Now, if you recall again, that Q is equal to C times V. Okay, by cross multiplying, we're going to have Q is equal to CV. Okay, if we substitute, we'll have C times V is equal to, now if replacing Q with CV, you have to remember that they're having the same potential difference. So instead of writing V1, write it as just V. So we're going to have C1 times V plus C2 times V plus C3 times V plus dot 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 plus Cn times V. Now all throughout again, V is constant, the same will factorize, and then we'll cancel it out. So V tends to cancel out every other V we're having here. So we'll now be left with the final value of C, or C total, will then be equal to C1 plus C2 plus C3 plus dot 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 plus Cn. Okay, now here is the formula we use to calculate the net capacitance for capacitors that are arranged in parallel. So you notice this is actually the opposite of that of resistance. Okay, when the resistance or when resistors are arranged in series, we tend to just add them directly like capacitors in parallel. And then when resistors are arranged in parallel, we'll do what now? Take the reciprocal of the sum, just like we're having here. Okay, so that is the major difference. Now most times in most textbooks or materials, we find that they gave something like a shortcut for solving resistance in parallel. Okay, that resistance in series rather. Capacitors, since we're talking about capacitors, let me leave out resistance. Now, for capacitors in series, instead of taking 1 over C total equals 1 over C1 plus 1 over C2 and so on and so forth, what we simply want to do most times is make use of some mathematical concept. We can just say 1 over, or rather, C total is equal to, there's a short called sum over product. Okay, Now, this sum of our products is something you need to have knowledge in maths for you to understand this, okay? So if, for example, we're having three capacitors, C1, C2, and C3, net capacitance is going to equal, remember the trick is sum over products. We're going to have C1 plus C2 plus C3 divided by C1 times C2 plus C2 times C3 plus C1 times C3. Okay, this is also another way. But like I said, most of you might not understand what I just did here. What you have to do is understand mathematical reasoning behind this. Okay, that's something you do in math. Okay, so for parallel connections of capacitors, we tend to just what now add them to get their net capacitance. And then for series connection, we take the reciprocal of the total connection and equate it to each of the individual one. Okay, that is how it's been done. In our next video, we're going to be solving a problem on capacitors and capacitors. So do it to stay tuned, like, share, and subscribe to our channel. Okay, like the video if you did learn something, and put it in the comment section if you have a question to ask. Okay, and if you also have something to say about the video, do it to put it in the comment section, or you have a video of a topic you want to talk about, put it in the comment section. Now, most importantly, like I always say, click on the notification bell so that when a new video is being uploaded or when I upload the next video, you'll be notified about it. Okay, if you don't get notified about it, most times or you tend to miss out on it. Okay, so take note of these things. Do it to like, share, and subscribe. Like I always say, to help me to create more videos for you guys. See you in the next video. Stay tuned.